Okay.
Hey, thank you, and thank you for the opportunity to speak at the seminar. It's nice to see that the tradition of the Greater Washington Topology Seminar is being continued. So, the goal for today's talk is to understand or say something about the Skein module of the connect sum of S1 times S2 with itself. Okay, so the outline is going to be as follows. So I will give some motivation as to why we study Skein modules. Then I will talk about arguably the most extensively studied Skein module of all, which is the Kaufman bracket Skein module. Give some examples, very few that have been computed, talk about some properties that we'll need to understand all of these results. And then finally, I'll touch upon a couple of conjectures, a computation of the connect sum of H1, that's two solid tori with itself. And then finally, I'll talk about this particular three-manifold. All right. So Skein modules are rather central in our study of quantum topology. The reason for this is that they are related to many fields of mathematics, for example, algebraic geometry, via SLNC, character varieties. They're related to hyperbolic geometry, via Teichmuller spaces. So there was some seminal work that was done in this case. So the first people to work on this were Doug Bullock, and then Adam Shikara and Joseph Chutitsky. And since then, a lot of people have kind of worked on this and extended their original work. So Teichmuller spaces, there's work by Helen Wang, so by Francis Barnahon, Helen Wang, and Tang Lei, where they constructed this quantum trace map from the Skein algebra, which basically relates the Skein algebra of a surface with the corresponding quantum Teichmuller space. They are related to cluster algebra theory. So this is by work of Greg Muller from the 2010s. Let's see some other examples so you can categorify them. So you can categorify Skein modules. This is by work of Asaida, Pshutitsky, Shikara, and it would be a shame to not mention the Witten-Reshetkin-Turai invariance. So this is work by Licorice and Blanchet, Hebeker, Maspom, and Vogel. And so there's plenty to go on here. They're related to Tempel-Lieb algebras, Hecke algebras, Hopf algebras. There's very rich representation theory here. So Skein modules are really kind of the bridge between quantum topology and knot theory and low-dimensional topology. And essentially, what all of these are that they are three-manifold invariants, and they're also link invariants for the links that live inside them. So there are two names that are synonymous with those of Skein modules. So the first one is Joseph Chutitsky, and the second is Vladimir Turaev. So Joseph Chutitsky discovered these in 1987, and shortly after, Turaev worked on these in 1988. The difference is that Joseph Chutitsky's first paper on this was a paper that kind of defines Skein modules in full generality, while Turaev's paper deals specifically with the Homefly PT Skein module and the Kaufman two-variable Skein modules, not the same as the Kaufman bracket, I think, as all of you already know. So the idea that Joseph has, as we all say, was to build an algebraic topology based on links. So the goal is that you want to generalize your polynomial link invariance for links in the three-sphere to an arbitrary three-manifold. We all know that all link polynomials for links in S3 have a defining Skein relation. And if you want to build invariance of three manifolds now, of links also, in not just the three-sphere, but in an arbitrary three-manifold based on these Skein relations, then Skein modules come into place very, very naturally. So there are several Skein modules that have been studied in literature. So there's the framing Skein module. For links in a three-manifold. I would say that joint with Diony Ibarra, Gabriel Montoya Vega, Josip Chititsky, and Deborah Weeks. We gave the complete structure of the framing Skein module for any three-manifold, any oriented three-manifold. There's the Homefly PT Skein module, which generalizes the Homefly PT polynomial for links in a three-sphere to an arbitrary three-manifold. There's the Dubrovnik Skein module. There's also the Kaufman Skein module, which generalizes the Kaufman two-variable polynomial. We all know that there's a substitution between their polynomials for links in the three-sphere, but it so happens that their Skein, the generalization, so that's the Skein modules, they're not equivalent for all three manifolds. Maciek-Myszkowski showed that for length spaces, these Skein modules differ. There is the Barnett and Skein module, which arises from Barnetton's study of covariant homology. The relations in this case involve surfaces and not links, as we would expect. There's also a four-dimensional generalization, rather recent, discovered about 4 or 5 years ago only. The Skein lasagna modules, which have elements of Skein theory and categorification mixed together, and you have a nice generalization of Skein modules to four manifolds with boundary and links in their boundary. Okay, so as I mentioned, the main object of my talk is the Kaufman bracket Skein module. Okay, so just some notation. Well, actually, maybe for this talk, I'll just skip this notation. Okay, so we'll always work with an oriented three-manifold. The reason is as follows. So if you recall, when you define your link polynomials, you work with link diagrams, right? So you have links in your three-sphere or in R3, and you project onto the plane or onto S2, and then your Skein relations involve diagrams of the links that you're working with. But now there's no notion of link projection in an arbitrary three-manifold. So what you do is that you think of links to be exactly the same outside of a small three ball in your three manifold. And inside that small three ball, they appear as various tangles. Oops. And for us to be able to distinguish this tangle from this tangle, so what's on the front, what's at the back, it will be essential to assume that there is some inherent orientation on our three manifold. So we will work with oriented three manifolds, but what the orientation is, what choice of orientation we use, that will not come up in this talk. Okay, our ring will be a commutative ring. with unity. And for our purposes, we'll work with the ring of Lorentz in
Rhea,
this way. Yes.
Rhea, you're not gonna say anything about the orientation, right? But does it matter? Does it affect the result depending on which one you choose?
No, it does not.
Okay, nice. Okay.
Yeah, good question. And the field of rationals. Okay. Um, So we'll be working over the ring of Lorentz and the field of rationals, or maybe one result about the ring of rationals where we invert all cyclotomic polynomials. Okay, so this is our setting: an oriented three manifold, a commutative ring with unity with an invertible element A. So this is an A, and some distinguished invertible element in our ring. All right. And this is how we define our Skein module. So what we do is that we take the free R module that's generated by ambient isotopy classes of unoriented framed links in our three manifold. We also include the empty link in here. Though for this talk, we won't really need the empty link, but when you want to define an algebra, then the empty link becomes necessary. Maybe I'll show one computation where the empty link really does become necessary for even modules. So we do include the empty link, though in its initial definitions, the empty link was not included. So the first relation is the coffin bracket Skein relation. So I will call this L plus minus A, ta-ta, minus A inverse, ta-ta, and I'll call this L naught. All right. So remember that we're working with framed links. So actually these should be ribbons. So you should think of, say, blackboard framing. So they should be ribbons or bands actually instead of just curves that I have drawn, but we will ignore the framing for now, but you should have it in your minds that there is a framing involved. Some people ask me often that, okay, if your manifold is oriented, then so do your links. Of course, that's true. There is an inherent orientation on the links as well. We ignore that orientation, okay? And so this is the coffin bracket Skein relation. And then we have the trivial component relation, which says that if you take the disjoint union of a link with the trivial framed link, then that is equal to the same link at the cost of a coefficient, which is negative a square minus a to the minus 2. Okay, and as I mentioned before, all of this is happening inside of a small three ball. All right, so you have tangles inside of a small three ball. And outside, the links agree. Inside, there are some different tangles, and they're tangles as shown. All right. There's also a third relation, which is the framing relation. So if you twist the framing by one positive full twist, that's the same as this, but it comes at the cost of this coefficient. But this one can be derived from the first two. Okay. So you take ambient isotopy classes of unoriented framed links in your oriented three manifold. This set is the generating set of your free R module, and then you mod out by the submodule generated by these two relations, and what you get is your coffin bracket Skein module. Okay, and as you might expect, this is not an easy algebraic structure to deal with. Calculations for this are incredibly hard. There are few examples that we know concretely, and moreover, calculations have been done over various rings: the ring of Lorentz, field of rationals, ring of Lorentz, where you mod out, where you invert all cyclotomic polynomials. So just some notation: when R is the ring of Lorentz, we will use just this notation. Okay, that's okay. All right. So here are some examples of I'm doing the timer. So here are some interesting examples of computations that have been done in the past. So the existence of the coffin bracket polynomial can very well be written just as follows: that the Skein module of S3 is free on one generator, and the generator is the empty link. So basically, it's just isomorphic to the ring of Lorentz. Okay. Then Jim Hoste and Josip Shutitsky in 1989, I believe, they computed the Skein module of lens spaces. And so they showed that the Skein module of lens spaces is free over the ring of Lorentz and has the floor of p by 2 plus 1 generators. Okay, and in this case, we assume that p is greater than equal to 1. Right? So for example, what this would mean is that the Skein module of RP3 has 2 generators, all right, because you have the empty link and you have one copy of your module is generated. So one of the generators is the empty link, and oh, has my screen stopped sharing? Hello?
No, it is totally regular.
Okay, because I got a notification that broadcasting has stopped.
It
Okay, now
stopped.
Now it is stopped. Now it is stopped.
Oh, okay.
The formula for lens space didn't end. It was kind of half
Okay.
only.
This is not good. Let me come back in. Sorry, we've hit a bit of a technical glitch for some reason. Let me join back in.
Mm-hmm.
I apologize. Okay, I think I'm back in. Let's see if I'm able to share. Okay, does everyone see this? So I
Yes.
shall repeat that
Yes.
Jim
Yes.
Hoste. Yes, okay, great. So I shall repeat that Jim Hoste and Josip Frititsky showed in 1989 that the Skein module of lens space LPQ is a free R module. They worked over the ring of Lorentz, and it has the floor of p by 2 plus 1 free generators. Okay, in this case, p is greater than equal to 1. I was mentioning what the result is for RP3. We know that RP3 is the same as L21. So that tells us from this result that it should be the floor of 2 by 2, which is 1 plus 1. So you have 2 generators. One generator is the empty link. One is the orientation reversing curve in RP2. Okay, a very interesting result, again by Jim Hoste and Josip Shititsky from a year later. This is about the Skein module of S1 times S2. So we should pay special attention to this one. So this has a nice cyclic decomposition. So it has a decomposition into free and cyclic modules of this form. So this is what the Skein module of this looks like. All right. So you see that it has this one copy of this free part, which is generated by the empty link. And then you have this infinitely generated torsion part. In fact, this is cyclic, all right? And the reason why this Skein module has such a decomposition and why there is so much torsion is due to the fact that this Skein module has a non-separating two-sphere. Okay. And whenever your 3-manifold has a non-separating two-sphere, the Skein module will always have torsion. The coffin bracket one will always have torsion because you can use the light bulb trick. The light bulb trick essentially gives us the following. You have a sequence of moves, all right, in which you get one link that intersects your non-separating two-sphere once. That, by sequence of ambient isotopies, gets transformed into a link where you've twisted the framing twice. And you just have to apply the Rademeister move twice, keep track of coefficients, because with each Rademeister move, your Kaufman bracket changes by a factor of a cube, and you get that your link equals a cube to the original link. All right, and that gives you your torsion annihilator, which is 1 minus a to the 6. And you see that when I over here is 1, you have this 1 minus a to the 6 appearing in this cyclic module. Okay, this will be important for us because the 3 manifold that I want to talk about, S1 times S2 connected some S1 times S2, has non-separating 2-sphere. So it has a non-separating 2-sphere, and so hence it's going to have torsion as well. Okay. Some other examples, say this is all work of Carrega, Gilmore. Well, they did it separately. So, and then their work was generalized by Cherry and Wolf. So the 3 manifold in this case is a closed surface times the unit interval. So the surface over here is closed. And then for the 3 torus, Carrega showed that there are 9 generators. So this was work by Carrega. And then that the fact that they're linearly independent was proved by Patrick Gilmore. And then later, this was generalized to closed surfaces of genus greater than equal to 2 times S1 by Cherry and Wolf. And they showed that this Skein module has 2 raised to 2g plus 1 plus 2g minus 1 free generators. So it's finite dimensional. So they also form a basis, so basis elements. But in this case, the ring that they worked with is the ring of rationals. So it's the field of rationals in this invertible element A. So essentially what you're doing is that you're killing all torsion, right? So as you can imagine, all of these 3 manifolds are going to have a lot of torsion, but if you work with the ring of the field of rationals, you will kill all torsion. So your Skein module essentially has no torsion, and in that case, they are able to find the exact list of generators, and they're actually linearly independent, so they have dimensions. So the dimension of the Skein module is 2 raised to 2g plus 1 plus 2g minus 1 when you work over the field of rationals. There are some other examples as well. For example, Patrick Gilmore and Harris, they computed the Skein module of a quaternionic manifold. But the ring that they worked over was the ring of Lorentz, and they inverted all cyclotomic polynomials. Essentially, even in that case, you are killing all torsion. And in that case, they show that for the quaternionic manifold, the Skein module has a basis that consists of 5 elements. Okay. So this is not an exhaustive list. There have been other computations done as well. Here is what I will talk about. So before I move on to connected sums, I would like to mention this very basic result, which we pretty much take as an axiom in Skein theory, which is the Skein module of a thickened surface. So Joseph showed that this is a free R module, which is generated by links in the surface. So links in our surface sigma that have no trivial components and no crossings. And this also includes the empty link. Okay, and in particular, this holds for handle bodies, because we know that handle bodies are thickenings of planar surfaces. So is the thickening of a disk with n boundary components times the unit interval. So essentially what this means is that, as an example, if I were to work with sigma 03 times I, so this is the pair of pants, then this is my pair of pants. Oops. And by abuse of notation, let me just call this the boundary component A3. This is the boundary component A1. This is the boundary component A2. And then what this tells me is that the Skein module of this 3 manifold, which is the genus 2 handle body when you thicken it up, this is free. It's infinitely generated by monomials of the form A1 to I, A2 to J, A3 to K, where I, J, K are greater than equal to 0. Okay, so these are monomials that generate the Skein module of the pair of bands, of the thickened pair of bands, which is the same as the genus 2 handle body. Okay, as a side remark, I would like to mention that Chebyshev polynomials of the second kind also form a generating set for the Skein module of this genus 2 handle body. And if just to remind you all, Chebyshev polynomials of the second kind are denoted by a capital S, and they have two initial conditions. S naught is 1. S1 of x is defined to be x, and they satisfy this recurrence relation. Sn plus 1 of x is x times Sn of x minus Sn minus 1 of x. And in this case, what you do is that you thread each curve into the variable. So your variable is actually a threaded curve, and the basis is basically, so let me write Si of A1, Sj of A2, and Sk of A3, where I, J, K are again greater than equal to 2, form the generating set of the Skein module of the genus 2 handle body. Okay. All right. So now we can talk about, so we've done some examples of the Coffin-Brackes Skein module. Next, let's talk about some properties of Skein modules, which will help us in our computations. So let's list out a few of these. So the first one says that Skein modules have an inherent functoriality, right? So if you have an orientation preserving embedding, so it's orientation preserving embedding of 2 oriented 3 manifolds, then that induces a homomorphism of the corresponding Coffin bracket Skein modules, all right? So basically, you have a functor from the category of oriented 3 manifolds with morphisms being, say, continuous maps into the category of modules over rings that have an invertible element, and then homomorphisms will be the morphisms. Okay, the second one says the following, that if you have a 3 manifold, so say you have a 3 manifold M that has a 2-sphere boundary, and you cap off that, so you fill in that boundary with a 3 handle, then you obtain a new manifold, say N, then essentially the associated embedding, because now M3 is embedded in N3, it's an orientation preserving embedding, it should induce a homomorphism between the corresponding Coffin-Brackes Skein modules, but in this case, it induces an isomorphism of the Coffin-Brackes Skein modules. So adding a 3 handle does nothing. Now say we start with a 3 manifold that has boundary. And on this boundary, you have some simple closed curve gamma, to the annular neighborhood of which you glue a 2 handle. Okay, you obtain a new manifold, say N. Of course, there is an embedding of M3 into N3, and this embedding will introduce a homomorphism between the corresponding Kaufman-Brackes Skein modules, but it's a little stronger. It's not just a homomorphism, it's an epimorphism as well. And the kernel of this epimorphism, so say, so let me call this I star, and this is my embedding I. Then the kernel of this epimorphism is given by handle sliding relations. So essentially, what this means is that the Coffin-Brackett Skein module of R3 manifold N is going to be isomorphic to the Coffin-Brackett Skein module of M, modded out by the submodule that's generated by elements of this form. Okay, so L will be an element that generates. So this belongs. So let me write it like this. This belongs to the generating set of the Skein module of M3, and this is the result of sliding our link across gamma. So the idea is that you could have two links that are not ambient isotopic to each other in the 3-manifold M. But the moment you glue a two-handle, you could slide one of those links across the two-handle and get that it's equivalent to the second link in N3. Okay. So essentially, you're killing the number of generators, right? Because now links are equivalent under two-handle addition. So this is encoded by these handle sliding relations. So just to recap, an orientation preserving embedding yields a homomorphism of Skein modules, 3-handle addition yields an isomorphism, and 2-handle addition yields an epimorphism. Why this is important for us is because of the following, that any compact oriented 3-manifold can be obtained from a genus N-handle body. So I'll call this HN. Okay. As follows, by gluing in, so by adding 3 handles and 2 handles. All right. And so what happens is that the generating set of the Skein module of your 3-manifold is the same as the generating set of the Skein module of a handle body. And from before, we know what the Skein module of a handle body is. And now we know what 3-handle addition does to Skein modules. It doesn't essentially change the Skein module. You have an isomorphism, but it does change the Skein module if you glue in 2 handles.
Hello? Hello?
Somehow I can't hear Rhea.
Yeah, me neither. Rhea, we cannot hear you. I think she left now.
I think Rhea is re-entering the room.
Okay.
Hello, I'm sorry. I don't know what happened. I think I got kicked out.
Yeah.
Right. And I didn't even realize I just kept on talking. So could you please remind me where you stopped hearing?
Just before Gunningham, Jordan, and Safronov.
Okay, all right. So it becomes essential to compute the set of handle sliding relations. And what I was saying was that arguably the most important property of Skein modules is a theorem by Gunningham, Jordan, and Safronov, proved in 2023. It was originally Witten's conjecture, which says that the Skein module of a closed-oriented three-manifold over the field of rationals is finite-dimensional. In fact, you don't need the field of rationals. You could just work over the ring of Lorentz by inverting all cyclotomic polynomials. You will still get finality. All right. Okay. There is so that is rather technical. It involves working with internal Skein modules and deformation quantization modules, so a lot of deep theory and factorization, homology, and so on. And there is a new proof, and moreover, their proof, so this proof by GJS is it's not constructive. So it really doesn't tell you what the dimension of the Skein module will be. It only tells us that the dimension of the Skein module is going to be finite dimensional, be less than infinity, but nothing more. So there is a new proof by Renard et Cherry and Giulio Belletti, which was put up on the archive in 2025, so just a couple of months ago, where they do make the proof algorithmic. So if you do follow their algorithm, it should be possible to compute the dimension of the Skein module over the field of rationals. Okay, but I'd like to mention that this is not true when you work over the ring of Lorentz. Okay, for example, we saw that Skein module of S1 times S2 is infinitely generated, right? It had that infinitely generated torsion part. So what really is the structure of the Kaufman bracket Skein module over the field of over the ring of Lorentz? There's some work that's been done in trying to understand this. So let's try to understand this work. So there was a conjecture by Julien Marché from 2019, I believe. What he said essentially was that this Skein module of a closed-oriented three-manifold, you work over the ring of Lorentz. This you can write as the sum of some number of free modules. So you have a free part, and then you have a torsion part. I don't want to go into too much detail. And this torsion part is essentially the following. So maybe here I should be a little more technical. So the torsion modules will be of the form n to the k, where these n to the k's are essentially a to the k minus a to the minus k torsion modules for each k. Okay. So what he conjectured was that if your three-manifold is closed, then over the ring of Lorentz, you always have a decomposition into free and cyclic parts. So we saw this for S1 times S2. We know that it has this one copy of this free part, and then you have this infinitely generated torsion part and cyclic. Let me go back in case you have forgotten. Where is it? Over here. So it has this infinity generated torsion part of the form a to the k minus a to the minus k, a byproduct of the proof of Cherry and Wolf. So their work on the products of closed surfaces with S1 shows that the Skein module of these three manifolds also has torsion of this form. So they were able to do it for closed surfaces times S1. Okay, but turns out that this is not true in general. So there is a counterexample. Which was given by RP3 connected sum RP3. Okay, so the structure of this Skein module is rather ugly. So it has two copies of free part, and then there's this third part, which is not torsion, it's not cyclic. All right. But interestingly, Chebyshev polynomials of the second kind make an appearance in the relations. Okay, so now we kind of get into the realm of connected sums. This was the first computation that was done for the Skein module of connected sums. And so the idea was that all of the examples before this satisfied Marchais' conjecture, but the moment you have connected sums, something goes wrong, right? And so this brings me to the first theorem that I wanted to talk about, joint with Tangley. And Josip Shititsky, hopefully in just a few days, not sure. And so what this says is the following, that the Skein module of this three manifold, which is the connect sum of two solid torus, which is genus one handle body, this is going to be isomorphic to the Skein module of the genus two handle body, modded out by relations of this form. Where k is even and greater than equal to 2. Why do we have this? So the reason we have this is as follows. So if you have your genus 2 handle body, then what we do is that we take the meridian disk that separates the two toroidal holes. So this is a meridian disk, and we take the boundary of this particular disk. We call this gamma, and to this we glue our two handle. Okay, so we started with H2, which is essentially the thickening of the pair of bands. So we know what the generators are. The generators are monomials of the form A1 to the I, A2 to the J, and then you have A3 to the K. All right. But now, the moment you've glued a two handle, you can slide links across one another. And the links are exactly, and the sliding relations are exactly of this form. So the ZK is just K parallel copies. So our ZKs are just K parallel copies that intersect this meridian disk K times, all right? And what we can do is that the handle sliding is very, very particular in this case. The handle sliding is of this form. So it is of this. So essentially what you've done is that you have taken your top strand and then you have slid it across the two handle. And the moment you do that sliding, you slide in this particular way. And you get this diagram. Now, of course, you can resolve this crossing and this crossing using Rademacher moves at the cost of coefficients, a cubed, and you will get this a to the 6 over here. Okay, so we know that handle sliding relations generate the submodule, which is the kernel of the epimorphism. We know that H2 is embedded in H1 connect H1. And so you have a homomorphism, which is now an epimorphism. Kernel is given by handle sliding relations, and handle sliding relations are exactly of this form. Okay. And another very interesting thing that happens, I don't want to go into the proof of this for the sake of time, but a very, very interesting fact that happens is that if I take K to be 2n, then for small n, we notice the following, that if we change the basis to Chebyshev polynomials, you might remember that the Coffin-Brackes Skein module of the thickened pair of bands, so that's the genus two handle body, is generated by Chebyshev polynomials as well. So if I do that change of basis, then we had relations of this form. So actual computations showed this. Okay, so let me just write for n equals 1 and n equals 2. You have -1, a to the 6 minus a to the -6, s2 of a3 plus a squared minus a to the -2 of s2 of a1 and s2 of a2 is 0. I don't think my Zoom is still sharing. Sorry, I'm facing a lot of tech issues at the time. Sorry, it's waiting to enter. Okay, so I will continue. So the idea was that for small n, we noticed that Chebyshev polynomials of the second kind make an appearance in the handle sliding relations. And there's an actually very beautiful, elegant formula for the presentation of these handle slidings. And it's still waiting to join. Oh, it's not connected. The Wi-Fi is a bit spotty. Sorry, just give me 1 minute. I hope you don't mind the delay. Okay, I think I am in again. So let me share my screen. Okay, all right. And you can go on like this. So for n equals 3, you're going to have a to the 8 minus a to the minus 8 times the third Chebyshev polynomial in the variable a3. And then this will change, this part will change to the third Chebyshev polynomials in a1 and a2. And so this was something proving this nice formula in terms of Chebyshev polynomials was something we were stuck on for a while, but we've been able to prove this. Again, joined with Tang and Yosef. And what we showed is that our handle sliding relations, which were of this form, essentially are exactly the same as, so let me write this in the next line. So minus 1 raised to n plus 1, yeah, curly n plus 1, the nth Chebyshev polynomial in the variable a3, plus curly 1, you have the nth Chebyshev polynomial in the variable a1 times the nth in the variable a2, where n is greater than equal to 1. And remember, k was 2n. Over here, curly k denotes a to the 2k minus a to the minus 2k. So really beautiful, elegant formula for handle sliding relations. So this also kind of goes back to the Skein module of RP3, connect some RP3. If you remember, I mentioned that Chebyshev polynomials of the second kind make an appearance there as well. The importance of this result is that if you want to compute the Skein module of any connected sum of a genus 1, so a Hilbert genus 1, 3 manifolds, you want to take 2 Hilbert genus 1, 3 manifolds, take the connected sum, compute the Skein module. These relations, these relations will exist in there, okay? And this brings me to what I wanted to talk about, which is the Skein module of S1 times S2, connected sum S1 times S2. So this is joined with, so this is me together with Songjung Kim, Changjin Shi, and Xiao Wang. Because that we compute the Skein module of 1 times S2 connected sum with itself. One motivation was that Sally Froman and Joanna Kanya-Bartoshinska were computing the Skein module of the K connect sum, and the handle sliding relations were just too difficult to deal with. And so we kind of took over from them, and we decided to do this one basic thing. So let me tell you what the structure is. I don't have that much time, so maybe just 1 or 2 results about this. So again, we start with our genus 2 handle body, all right? But now if you want to construct S1 times S2, where you do it is that you take the meridian, you take the meridian disk here, you take the meridian here, you take the boundary of this meridian disk, the boundary of this meridian disk. So let me call this beta, let me call this say eta, and to these you glue 2 handles. Right? So now you have 2 handle sliding relations coming from this handle, you have 2 handle sliding relations coming from this 2 handle. You have to make sense of those 2 handle sliding relations. And essentially what we did was that we computed the submodule of handle sliding relations for the Skein module of this particular 3 manifold, and a very important feature that it has a succinct presentation in terms of Chebyshev polynomials in the second kind. So of the second kind, sorry, of the second kind. This was, of course, quite hard to prove. It's also very, very technical. The paper's up on the archive. You can look it up. But essentially, the idea is that, so we tried to work with the relative Skein module to obtain the Handelslight and that. We kind of did it by brute force by the end of it, but we have a very excellent presentation in terms of Chebyshev polynomial of the second kind. But the result that I want to talk about and finish with is the following. So we all remember that the Coffin-Skein module of S1 times S2 imputed by Joseph-Prititsky is infinitely generated, right? It has that one copy of the free part, infinitely generated torsion part, which is cyclic in nature. Okay. Kind of going back to Marchais' conjecture, which talked about a decomposition into free and cyclic part. What we showed is that the Skein module of this connect sum does not split into the sum of free and torsion submodules. So not even cyclic, but not torsion also. So something stronger than what we had for RP3 connected sum RP3. Okay, so it's not just cyclic, but not torsion either. The proof was so the proof is not that hard. It's a little technical, so maybe we can skip that for time. But what I'd like to mention is that this Skein module, so again, joined with Shang Horowitz Kim, Shangjin Shenwang, we show that the Skein module of S1 times S2 connected sum with itself has torsion elements. So essentially, this makes the module very, very hard to understand because you don't have decomposition into free and torsion modules, but you do have torsion in it. So how does that sit inside of the Skein module? So we found two families of torsion elements. So the first family is annihilated by the element 1 minus a square. So they are 1 minus a square torsion elements. And the second family, let me say they're the family of torsion elements that are kind of not killed by the connected sum operation. So the crux of the matter is that the Skein modules of connected sums of three manifolds are very mysterious because we don't expect them to have this nice decomposition into free and torsion modules like we have for, say, prime manifolds, though even that is a conjecture. But what's even more mysterious is that even though you don't have this decomposition, you still have torsion appearing in them, right? So for example, RP3 is like that, RP3 connect sum RP3 is like that, the connect sum of two solid tori is like that, the connect sum of S1 times S2 with itself is like that. And therefore, now we have ample evidence for this conjecture. So we conjecture, this is something that we're currently working on, that the Skein module of two closed-oriented three manifolds over the ring of Lorentz does not split into the sum of free and torsion modules. Okay, so this is our conjecture, something that we're working on. Some odds and ends. You might wonder, what about other connected sums? Say, what if, so this was for closed three manifolds, right? This is M and N over here are closed three manifolds. What about manifolds, so compact manifolds with boundary? So for that, we would need to understand first The connected sum, so this is arbitrary, of course, the connected sum of arbitrary genus handle bodies. So this is HN connected sum HM. There was a result about their structure. In particular, the results said that, as some of you may already know, that only one type of handle sliding was enough, which is that handle sliding on the top arc, and that's it. But turns out that is not true. We need more handle sliding relations, which we are unsure of at the moment. No one knows how many handle sliding relations you need, even say for H2 connected sum H1. So no one knows. So that would be the first thing that you'd need to do to understand arbitrary connect sums. You'd also need to compute the K connect sum of H1 with itself, because we know that if you compute the Skein module of this, then if you glue 2 and 3 handles to the meridians at each toroidal hole, then that would give you a 3-manifold, which is a connect sum of so just like S1 times S2 connect sum S1 times S2, this would be the building block for the K connect sum of S1 times S2, for example. So you would get arbitrary connect sums. And this is also an open question. No one knows what the Skein module of this is. Okay, so I will stop here. Thank you very much.
Okay, let's thanks Rhea for the great talk.
Thank you.
Thank you.
So I have a quick comment, interesting comment. So our next speaker on October 15th would actually be your co-author Sin-Jong Kim.
Excellent, amazing. So do you know what he's talking about?
I don't.
What is
I
he
told
talking
him it's
about?
not rushed. I
Oh,
told
you
him it's
don't.
not
Okay.
rushed. He can send me
Okay.
the topic within a week, so I haven't received any.
Okay. All right. Great. Excellent. Thank you
So
for
where is
telling me.
he
I'll
now?
be there.
In China or in Korea?
Yeah, he's in China.
Jilin.
Yeah, he's got a
Okay.
permanent position.
Okay.
He's doing.
Nice.
Yeah.
Okay, so anyone got any questions?
Are you guys, or what do you feel? Are you guys close to proving this conjecture? Or what do you think? Yeah.
It's hard to say at the moment because this is a very strong conjecture. Again, just like in Skein theory, we have a few ideas. One of them didn't work out, so now we're trying the second idea. That's where we are. So hopefully, let's see what happens. But yeah.
Even older conjecture, which is much weaker, that this connected sum have torsion at all, is not finished. It is proven in almost all cases, but still not always. Not for
I
all
think
cases.
now and Giulio proved it for connect sum of a lens space, which is not RP3 with RP3, and they show that it does have torsion.
So it's closer and
There's
closer.
some work by Raphael Zentner and Steven Sivek, and I forget the third author, where they use some Cyborg-Witten tools to get torsion in some connected
Because to
sums.
guess what is torsion element is not difficult, but to prove that is not trivial was causing trouble. But you're right, there are better and better technique. I started from homology, then it was SL2 character, and then, as you said, they use more
You
sophisticated
need
tools.
some other techniques. So just standard algebra, brute force computations aren't gonna work.
Are not sufficient, yeah.
Yes.
Mm.
So what Raphael Zentner, Steven Sivek, and their co-author Shodip Ghosh, they showed that the coffin bracket Skein module of a non-3 prime manifold has non-trivial torsion when 2 of the prime summons are different from RP3. So basically, when you're not working with RP3, then the connected sum will have torsion, but we don't know whether it still spits into the sum of free and torsion modules. I think Renaudet, Cherry, and Belletti improved this a little. They were able to show it for one RP3 connected another lens space, which is not RP3.
Yeah, okay, so closer
But
and
other
closer.
than that, yeah, so closer and closer, but just knowing whether torsion exists or not is not enough. You need to know the exact structure, because as we saw, you can have torsion and still not have this decomposition. So, yeah.
Okay,
And
any
you
other
guess that
questions?
never you have, yeah.
All right, let's thanks our speaker again, and then we go to coffee chatting time.
Perfect place. Okay, let's go to drink coffee. Now too late.
I have
Decaf.
to, sorry, I have to rush. I have to be somewhere. I'm already late. So I will have to leave, but I will see you on October 15 for the next talk. Thank you for attending, whoever attended, Lisheng, Diony, Carlos, Alan, Ali, Gabriel, Yosef. Thank you so much. I shall
you.
stop.